Someone check if it's working. Hello, am I audible?
Yeah,
Hello,
we are live.
we are live, right? Okay, cool. Record. Record to the cloud or computer?
Do it to the cloud. Or if you do it to your computer, then it will be saved in your laptop or PC.
I'll just share. I'll just upload it on the drive after. Okay.
I mean, you can do it on the cloud as well. We have enough storage, but whatever is
Okay.
preferable.
I'll just do it on the cloud. Unable to contact the meeting host or their account admin. I'll just record it on the computer because I think can you record it, because then I think you can upload it on the I can't upload it. Are
No, you will have to record it to the computer. It seems that the cloud is full. I don't know how.
okay, I'll record it. Done. Okay, so I'm going to disable the waiting room and people are going to enter. When the professor enters, let me know. I'll make them the okay.
Let's do the talking on WhatsApp, not here maybe.
Hello, sir. We are Naxatra. I'm Atuja. Sir, we will start the meeting in some.
Can you hear me?
Yes, sir. Yeah, we can hear
Okay,
you.
all right, yeah.
Yes, sir.
Okay, until now I was not able to
Yes, sir.
unmute. Okay.
A very warm good morning to one and all present over here. I think I am audible. Yes, maybe.
Yes, you are audible.
Thank you. We are Naxatra, the Astronomy Club of Isa Berampur, and we welcome you all to the workshop on X-ray astronomy data analysis. We are thrilled to have you here as we explore this fascinating world and its latest advancement and technologies. We are honored to have a lineup of distinguished speakers who are pioneers in astrophysics and data management. So, at first, I want to welcome Dr. Srinath Ratnakumar. A workshop of this level was only made possible with the help of Dr. Srinath Ratnakumar, who is our main coordinator. Dr. Ratnakumar is a highly accomplished scientist at the Indian Space Science Data Center, ISRO, with expertise in space data management and analysis. So I want to hand over the mic to Chetan now. Chetan, please.
Hello, good morning, sir. I'm Chetan from Naxatra. And now we would like to welcome our first speaker today, Dr. Dipankar Bhattacharya, an esteemed professor of astrophysics at Ashoka University in Haryana. Dr. Bhattacharya is a distinguished astrophysicist with prolific career spanning several decades. He has made significant contribution to our understanding of high-energy astrophysics, particularly in the study of neutron star, pulsars, and black holes. His research has been instrumental in advancing our knowledge of these enigmatic celestial objects and their underlying physical processes. In addition to his research, Dr. Bhattacharya is also deeply committed to education and mentorship, inspiring the next generation of astrophysicists through his teachings and guidance. In this talk, Dr. Bhattacharya will give an overview of X-ray astronomy. Yes, sir. You may start.
Thank you very much. I'll try to share my screen now. I hope you can see my presentation full screen.
Yes, sir.
All right. So thank you very much for inviting me to this workshop. It's a pleasure talking to all of you. And I will today I'll just try to cover as the opening talk of the workshop a broad overview of X-ray astronomy. So I'll not go into any nitty-gritties of either the data structure or data analysis, which we will hear in the presentations and sessions to come. So let's begin. So X-ray astronomy, by definition, means observing radiation from cosmic sources in a region of wavelength which falls as we classify as X-rays. Now, it so happens that our atmosphere provides a very protective layer for us. So it absorbs most of this high energy radiation. So if we're looking at some cosmic object which is radiating in X-ray bands, the upper atmosphere and in the atmosphere as a whole is able to stop these X-rays from reaching the Earth. On the other hand, the visible band, which you can see here, can come all the way down close to the ground, and the radio band can also come all the way down, come close to the ground. So, in visible band, the optical band, and the radio band, you can easily do astronomy based on the surface of the Earth. But since X-rays will not penetrate the atmosphere, as you can see, the atmospheric capacity is about 100% in these X-ray range. The X-ray astronomy is only possible if you put up detectors or telescopes in space. So space-based platforms are required to carry out X-ray astronomy observations. So therefore, the development of X-ray astronomy has gone hand in hand with the development of space technology. Astronomy itself is a very ancient science. Humans have been looking at the sky for time immemorial, trying to understand what the objects are composed of, how do they move, what goes on inside them. But most of that has been done with ground-based observation until very recently. So X-ray astronomy, astronomy at high energies really only began in 1962 when from a rocket platform, Riccardo Giacconi discovered X-ray emission from outside the solar system. One of the first sources to be discovered was Scorpius X1, which was a neutron star accreting material from a nearby companion star. So this is now just about 60 years old, as opposed to the rest of ground-based astronomy, which is millennia old. So we consider X-ray astronomy as one of the young branches of astronomy. So to carry out astronomy at X-ray wavelengths, not only would you have to put up platforms outside our atmosphere, so in space, you also need to put together detectors which can capture and measure properties of these high energy photons. And measuring photons at high energies as well as high energy particles has been the domain of particle physics for quite a long time now. So X-ray astronomy therefore borrows from both these areas. It borrows from particle physics for sensors and space technology for providing an observing platform. When these two come together, we have a capable X-ray astronomy telescope cum detector, and we put them up in space to observe objects which are emitting X-ray band. We have, for example, shown one of the iconic X-ray observatories of NASA, Chandra X-ray Observatory, and our own Indian observatory, AstroSat, which was launched by ISRO in 2015. Chandra X-ray Observatory has just completed 25 years in space on 23rd of July this year. And it's still one of the prime X-ray observatories that is available for people to use. How do X-rays get produced in cosmic sources? And this decides what kind of objects we can see in X-rays. Most of the normal stars that you can look up in the sky at night are not bright X-ray objects. So, X-ray sky, if we had X-ray eyes, would look actually very different from the optical sky that we normally are used to. So, ultimate X-ray emission actually requires either very hot gas, the thermal X-rays, the temperatures exceeding a million degrees or so. The very outer layers of the sun, the solar corona, happens to be very hot. Although the amount of material there is very little, the corona happens to be very hot. So the corona is an X-ray emitter. So solar X-rays come from the coronal regions. But the total amount of X-rays emitted by the sun is quite small compared to other X-ray sources, cosmic X-ray sources. And that's because although the gas is hot, the amount of gas in the corona is very little compared to the total mass of the sun. But there are other areas where large amounts of hot gas are found, and I will come to some examples in the coming slides. There is also another mechanism which can produce very highly energetic electrons, which then radiate their energy in X-ray band. So this could be a non-thermal process where the energy distribution of electrons assume a shape which is not like the thermal distribution, where energy distribution is Boltzmann. The non-thermal distribution could be some other shape. Most often, it is seen to be a power law. And these electrons become highly relativistic. So, their kinetic energy far exceeds their rest energy. And this can happen in regions where accelerating electric fields are available. We'll see some examples where this can happen. Or you have electrons moving in a region which has magnetic irregularities, which are in motion with each other. So these are two different ways where you can produce sufficiently energetic particles which then end up producing X-ray emission when they radiate. Compact objects such as neutron stars and black holes are prolific sources of X-rays because both these processes can take place very efficiently near these objects. The extreme gravity of neutron stars and black holes causes any external gas that can fall onto these objects to get very hot because of the large amount of gravitational potential energy that can be released. And these objects, particularly neutron stars, are also endowed with strong magnetic fields. And when a neutron star like that rotates, for example, or undergoes a crust quake, then this magnetic field is in motion with respect to the surroundings, and that causes very strong electric fields which can accelerate electrons to very high energies. So the compact objects that we're talking about are actually remnants of the evolution of stars. So when a star exhausts all the nuclear fuel that it can burn at the center. Eventually, the core of the star condenses or collapses from a very compact object. Depending on the initial mass of the star, there are three different possibilities of the compact remnants that can be produced. The lowest mass ones would leave white dwarfs. The mass of the white dwarf itself would be less than 1.4 times the mass of the sun. 1.4 times the mass of the sun happens to be what we call the Chandrasekhar limit, that is the upper mass limit of a white dwarf. And this will be composed mainly of either helium at the very lowest end of mass, or carbon oxygen in the middle range of mass, or oxygen and magnesium at the highest range of masses. However, if the original star had a much larger mass, then the core also will acquire a larger amount of mass before it condenses. And now that the core mass has exceeded the mass limit of a white dwarf configuration is no longer possible to provide a balance. And then the core condenses to a much tighter, much more gravitationally bound object. It could be either a neutron star, where the mass limit is roughly about 2.5 times the mass of the sun. So if the remnant compact object has a mass in the range 1.4 to 2.5 times the mass of the sun, then you will get a neutron star, which is mostly composed of neutrons plus some fraction of protons, electrons, and other exotic particles. Now, if the compact star mass happens to exceed even the upper mass limit of neutron stars, then there is no choice but the gravity will have the ultimate triumph, and all the matter will get squeezed to a singularity surrounded by event horizon, and this is what we call black holes. The process of producing either a neutron star or a black hole happens to be quite violent, accompanied by explosive events such as supernovae or gamma ray bursts, which then expel matter, the outer parts of the star, at very high speeds. In case of supernovae, the matter could be expelled at speeds of the order of 10,000 kilometers per second. In gamma ray bursts, some part of the matter is expelled like in the supernova, but some fraction, a small fraction of the matter, can be expelled at an extremely high speed, very close to the speed of light, causing a relativistic jet to be produced. Now, all these effects have sufficiently energetic material that can give rise to X-ray emission afterwards. So one of the ways ultra hot gas can originate is by the shock wave that would be sent by the fast expanding material out of a supernova explosion. This material is moving at a speed thousands of kilometers per second into a medium, which is the interstellar medium, in which the sound speed is only about 10 kilometers per second. So this expanding fluid is moving at a speed which is between Mach 100 to 1000. And such a thing will obviously create a very strong shock. And material crossing the shock then gets heated to very high temperatures. And this shock heated material can produce thermal emission at X-ray wavelengths. And most of the young supernovae and supernova remnants are actually pretty bright in X-rays. So this is, for example, an X-ray picture of a supernova, which took place in our galaxy as seen by us in 1006 AD. And this is a picture from the Chandra X-ray Observatory. And all of this emission in the interior that you are seeing is from hot gas heated by the shock waves. Heating can also occur by magnetic processes, and our sun is an example. The sun, as you know, has many sunspots, particularly now, at the peak of the solar cycle. And these sunspots are concentrations of strong magnetic fields. And around these sunspots, you have magnetic reconnection and other magnetic processes going on, which release bursts of energy into the gas that is embedded in. And this gas then redistributes that energy by raising its own temperature. And this is mainly the mechanism by which the solar corona, which you can see in the outside here, is heated, and also the active sunspot regions contain this very hot gas. And an X-ray image of the sun, as you can see here, the solar disk itself is quite dark, but the hot gas, which is the corona and the active regions, become bright spots in X-rays. And this is a magnetic heating process. Another way outer hat gas is commonly produced is by having a compact object in a binary system with another star, which could be a regular type star, or even another compact object. So material can flow from this donor star to the other compact object. The material will normally try to flow in a spiral fashion because the orbital angular momentum needs to be gradually dissipated. So the matter will spiral in and approach the compact object and fall onto the compact object. As the matter moves from outer parts of the accretion disk to this compact object, more and more gravitational energy is released, and the material gets hotter and hotter until it either falls on the surface of the compact object, or in the case of black hole, disappears within the event horizon. So the hottest parts of the disk are the closest to the compact object. As you go out, the disk is cooler. And these hottest parts of the disk are hot enough to produce X-ray emission. And these type of objects happen to be the brightest X-ray sources we see in the sky. Yet another way of generating hot gas is by thermonuclear reaction. Consider a compact object which is accreting material. Of course, the disk is hot. Some of this disk is producing X-rays, but the matter is eventually accumulating on the surface of the compact object. It could be either a white dwarf or a neutron star. After the accumulation of some amount of material, the conditions become right for the accumulated material to undergo nuclear fusion. So for example, if a mixture of hydrogen and helium is being accreted on the surface of a white dwarf, then after a point, hydrogen will ignite, and then helium will ignite, and sudden burst of thermonuclear fusion energy can then cause the object to get the gas to get heated to very high temperatures, and you can see a flash of X-rays. Could be true for either white dwarf or a neutron star. So in case of white dwarf, this will be called a nova explosion. In case of a neutron star, it will be called an X-ray burst. This turning into a flash is another way of producing very hot gas. Another very important region which tends to produce huge amounts of very hot gas are at the centers of clusters of galaxies. If you have a cluster of galaxies, you have a large number of galaxies which are bound together by the gravity of the cluster, but the main source of the gravity of the cluster is not the galaxies themselves, but the condensation of dark matter within the cluster. And this condensation of dark matter exerts a very strong gravitational pull and produces a very deep gravitational potential well. So diffuse gas in the cluster then tends to be attracted to this gravitational potential well, falls within the gravitational potential well, and gets strongly heated enough to produce copious amounts of X-ray emission. So clusters of galaxies produce lots of thermal X-rays over large regions because of the presence of this strong concentration of dark matter. So these are some examples of how X-rays can be produced by thermal gas. Non-thermal emission requires charged particles to be accelerated to very high energies, and possible sites for those. One of them certainly is a spinning neutron star, spinning magnetized neutron star like a pulsar, where to an observer you can see if the neutron star has a dipole magnetic field like this and it is spinning, there is a varying magnetic field at any point in space, and the varying magnetic field is akin to a strong electric field, and this strong electric field will accelerate any charged particle that may be present in that region, and the combination of strong magnetic field, Teragauss fields in a pulsar, with fast spin, which is of the order of a second or even faster, can produce extremely strong electric fields going up to 10 raised to the power of 12 volts. And therefore, any charged particles placed in such a condition will be accelerated to extremely high energies in electron volt or more. And since the rest energy of an electron is only less than a mega electron volt, these become highly relativistic. And these relativistic particles then move in the local magnetic field and produce various kinds of emission, particularly synchrotron emission, or if the particle is moving along the magnetic lines, then it will produce curvature emission. So these emission processes then lead to high energy photons being emitted, X-rays being among them. This is a picture of a supernova remnant. The supernova occurred in 1054 AD, and at the site of the supernova now sits this spectacular remnant where this is a composite picture of various wavelengths. These filaments are in optical, which is showing the expelled matter, but there is this diffuse glow at the center. The red is in infrared, and this white is in X-rays from Chandra Observatory. This diffuse glow actually comes from the highly energetic particles that have been produced at the pulsar that is at the center of it, and then the particles have drifted into the interior of the supernova element. And they now produce this high energy emission in the local magnetic field. It's a synchrotron emission in the strong magnetic field that is present. So this is an example of a huge amount of non-thermal emission that is being generated by high energy particles. We talked about supernova remnants and the shocks that they drive in the external medium. Of course, the material that crosses the shock gets heated, so you get strong thermal emission from such material. But there is also another process that the shocks lead to, and that is if you have energetic electrons that can scatter from magnetic irregularities around the shock, and they can go back and forth, cross the shock multiple times, then in each crossing, the electron gains some energy, and over many crossings, the electrons can get to very highly relativistic energy. And these again then form a bunch of electrons that produce non-thermal emission in the local magnetic field in the shock. And in this picture, all this interior emission that you're seeing in X-rays, this is again an X-ray picture of a supernova remnant Cassiopeia A. All this is thermal, but this blue rim of emission is non-thermal, as can be distinguished by its power loss spectrum compared to thermal spectrum of the rest of the emission. Finally, in case of a black hole or a very strongly magnetized neutron star, as the accretion disk of external material approaches the black hole, if there is a strong magnetic field present, then the material can be flung by the interaction with the magnetic field and be thrown out in the shape of highly collimated jets. And these jets will then contain particles which are accelerated by this magnetic process, which will also have a non-thermal distribution. So the emission from jets normally have a non-thermal spectrum, and so they are composed of electrons and sometimes electrons and positrons, which are accelerated by this electromagnetic process. So these are various possible ways X-rays can be generated in cosmic objects. And to observe them, we can study them in multiple ways. The four main techniques that we normally employ are imaging, spectroscopy, timing, and polarimetry. So these are just intensities as functions of different things. Intensity as a function of position in the sky will create an image. Intensity from a source as a function of wavelength, which in X-rays we refer mostly as photon energy, will give you spectroscopy. Intensity as a function of time will give you timing, and intensity as a function of polarization state will give you polarimetry of the source. And there are different missions which have been designed to optimize one or more of these techniques. So this is a compendium of some of the active X-ray astronomy missions which are working today. I mentioned already the Chandra X-ray Observatory. This is by far the best imaging mission that exists. with highest resolution X-ray imaging that is possible today. There's also a large mission which has also been flying for decades now, that is XMM Newton. Both these do imaging and spectroscopy combined. Not so much fast timing. Then there is SWIFT, which is a multi-wavelength platform, including X-rays, which is primarily designed to follow transient objects in the sky, like gamma ray bursts, but it can also do many other things. Chandra is a NASA mission, SWIFT is a NASA mission, XMM Newton is an ESA mission, European Space Agency. And going to higher energies, another very capable mission that is currently operating is called NuSTAR, Nuclear Spectroscopic Telescope Array. And that works up to hard X-rays, about 80 kiloelectron volts, and is very capable in doing spectroscopy at these high energies and some amount of imaging. There's also, this is again a NASA mission. Then we have InSight HXMT. This is a Chinese mission. This hard X-ray modulation telescope. So this has been surveying the sky at hard X-rays and also performing high resolution timing and some amount of spectroscopy. This NICER mission, this is the NICER mission above the International Space Station. NICER stands for Neutron Star Internal Composition Explorer. So this is specifically designed to do fast timing and good spectroscopy at soft X-ray band. And main targets are neutron stars, and the idea is to observe them well enough to put constraints on the mass and radius of neutron stars. We have our own astrosat. You will hear more about it in the coming lectures. So NICER again is a NASA mission. Astrosat, of course, is an ISRO mission. Recently launched last year is a Japanese mission called PRISM. This is X-ray imaging and spectroscopy mission. So this has the highest spectral resolution ever flown in X-ray bands. It uses a device called microcalorimeter, which gives you extremely fine spectral resolution of the order of an electron volt or so. And it has some amount of limited imaging capability also on board. And its primary objective is to obtain high resolution spectra of X-ray sources. Just one of the newest launches that has been is this SWAN mission, which is a European-Chinese mission. By the way, PRISM is a Japanese mission, I forgot to mention. It's a JAXA mission. SWAN is a European-Chinese collaboration. The Space Variable Object Monitor. This is also a mission which is primarily designed to follow gamma ray bursts and study their spectra and timing in detail. IXPE is a novel mission which was launched in late 2021. It is to study polarization in X-rays. So it is X-ray polarization explorer mission, imaging X-ray polarization experiment. And so this has some amount of imaging capability, and it has got a polarization sensitive detector, which then is able to obtain polarization at X-ray energies between 2 to 8 kilo electron volts. In January this year, ISRO launched Indian polarization mission XPOSAT, X-ray polarization satellite. This carries a polarization telescope called POLIX and also a spectroscopy detector called XPECT. So this is currently in performance verification phase and will be open for science observations soon, I presume. And so this is designed to detect X-ray polarization in the range of above 10 kilo electron volts or so. So this is a complementary observation to IXPs. So these are some of the X-ray missions which are actually actively operating now, and if people are interested, they can apply for time and obtain data using any of these missions. As I said, there are 4 different dimensions of X-ray astronomy, starting with imaging. Just some examples. The best imager, as I said, is Chandra, which just completed its 25th anniversary, and NASA has released 25 iconic images taken by Chandra over its 25 years in celebration of its 25th anniversary. And this is a collage of these 25 images. You can see the range all the way from planets to the clusters of galaxies, so the vast scales. I'm not going to the details of each of these images, but anyone who is interested can peruse through this NASA release and learn more about the imaged objects. But one can just admire the detail and depth to which these images have been obtained. This is an all-sky image in X-rays, particularly showing the X-ray emission from our own galaxy. This has been taken by a survey mission called eROSITA, which was launched in 2019. It's a European-Russian collaborative mission. But since 2022, the mission has been dormant. It is not operating because of political differences between Europe and Russia. But in the couple of years of data that was taken, it has produced spectacular distribution of X-ray emission over the entire sky, showing galactic plane and these big plumes around the galactic plane where very hot gas as well as non-thermal gas is present. Examples of spectroscopy. This is a spectrum as obtained by Chandra X-ray Observatory. Chandra X-ray Observatory is an imaging telescope, but it also has a grating. So the grating can disperse the image in and produce a trail as a function of wavelength. So this is a 0th order image where all wavelengths are together, and then this is the spectrum, dispersed spectrum. So you can see the image is replicated at various wavelengths, where specific strong emission exists. So you can see that at some narrow bands of wavelengths, you have strong emission, and those correspond to different spectral lines of different elements. So this allows you to find the composition of the gas which is present in the supernova remnant, and not just that, the distribution of material of these different species within the gas. In many other cases, spectroscopy can be done by measuring the energy of individual photons that are detected, and then giving the counts as a function of energy. And most X-ray spectroscopy is done that way. This is another example of spectra taken from new star and a mission that is no longer operating now, Japanese mission called Suzaku. And this is a spectrum of an active galaxy. And what you see here is the iron line of 6.4 keV, but the iron line has a trail at lower energies, and this trail is caused by the motion of gas very near the central black hole. The Doppler shift produced by this motion draws out the inner edge of this line, and the overall line is also shifted because of the gravitational redshift from the black hole. So by studying the profile of this line, one can estimate both the mass and the spin of the accreting black hole. Another recognizable feature in X-ray spectra from neutron stars, particularly strongly magnetized neutron stars, happens to be cyclotron lines. So resonant absorption at cyclotron line frequencies can take place in the magnetospheres of neutron stars, the atmospheres close to the surface. And this specific energy is indicative of the magnetic field strength of the neutron star in the emission region. This is a good way to measure magnetic fields of neutron stars. If you do broadband spectroscopy, combine X-rays with other wavelengths, and this, for example, is of a bright active galaxy, the blazar. And then this broad spectral energy distribution allows us to separate different emission mechanisms. For example, there is synchrotrons, seed photons, covering radio, optical, and X-ray. And in gamma rays, you have these seed photons being comptonized and raised to higher energies. So X-rays, as a part of broadband ACD, can provide very valuable information about the radiation processes. Coming to timing, what we need to keep in mind is that the brightest X-ray sources are compact objects. And these compact objects, no matter whichever telescope you use, the angular resolution is not enough to resolve the processes near the compact object. You cannot image them. So they will always look like a point object. So if you want to study either the nature of the compact object or the flow, one will have to do it through other means. Spectroscopy is one of them, and timing is another. The most such objects display strong time variability. If you look at the image on the right, I'm going to go through a 21-month sequence of the image of the same region taken by the Chandra X-ray Observatory. And you can see from one image to another, in a few months, there are major changes in which objects are visible, which objects appear, disappear. And this is because each of these objects is strongly variable in its intensity. So most such compact sources display strong time variability over a large range of time scales. It could be milliseconds to years. And the study of this timing can reveal a lot of information about the nature of the flow of the matter as well as the nature of the compact object itself. For example, let's take this object. This is ultraluminous X-ray pulsar in M82 galaxy, and this observation taken by NuSTAR, and you can see the object pulsing regularly at 1.37 seconds, which then happens to be the spin period of this X-ray pulsar. So this has told us that this object must be a spinning movement. The form of intensity variation as a function of time can take many shapes, and can take many shapes even within the same object. This is the rich variety of temporal variations of intensity seen in one compact object at different times. This is GRS 1915 plus 105, being a black hole X-ray binary that has been studied in great detail. And you can see at different times, you get very different patterns of time variability. And a certain pattern tends to persist for a while and then move to a different type of time variability. And this carries a wealth of information about the accretion flow. Some of this time variability can be quasi-periodic in nature. So if you look at the fluctuation spectrum as a function of fluctuation frequency, then you see that there are specific frequencies where the response could be quite large. And so these are not exactly periodic. Exactly periodic would be very sharp spike over there, but this is nearly periodic with a certain width. So they're called quasi-periodic oscillations, and they relate to several normal modes of the flow or the compact star and the flow combined. A detailed study of these quasi-periodic oscillations can provide the measure of mass and spin, particularly of a black hole, which may be undergoing this accretion. If the accreting object happens to be a strongly magnetized neutron star, then the matter interacts strongly with the magnetic field and then is guided by the magnetic field onto the surface. And the region of this interaction can cause additional types of variability in the flow, which can manifest themselves as intensity variation in the X-ray emission. And if you look at the power spectrum of such binaries, particularly with low mass X-ray binaries with neutron stars, then you get specific features like this quasi-periodic oscillation, bumps over here, the noise, broadband noise over there, and very interestingly, quasi-periodic oscillations at very high frequencies like kilohertz. And these carry information which is a combination of the mass, the spin, the radius, and the magnetic field of the neutron star. And with sufficient observations, constraints can be placed on these quantities of the compact object. I mentioned NICER as a mission which has the objective of trying to place constraints on the mass and radius of neutron stars. They're trying to do that by doing very detailed and very accurate observations of X-ray pulsars. One of them is this J0 for 37 minus 4715. So this is non-accreting X-ray pulsar. So it's emitting X-rays because of magnetic magnetospheric processes which produce highly energetic particles, some of which go back and strike the surface of the star, and the surface of the star becomes hot. And this hot spot, as it spins around, we see a variation in the X-ray intensity that comes to us. So a detailed study of this variation pattern at different photon energies. So this is spectroscopic study at the different photon energies. The time variation at different photon energies, spectrotiming, can then reveal a lot of information regarding the spin of the neutron star and how far the spin actually contributes to Doppler shift. And the Doppler shift is related to the actual linear speed, the circular speed of the hotspot at the surface, where the spin rate is something that we know from the spin period. And the combination of this circular speed and the spin period actually gives us a radius. So this gives you information about the radius, information about the mass, information of the mass, because there is a gravitational light bending that is involved, and light bending, degree of light bending depends on the compactness of the object, mass by radius. So putting all this information together, one is now able to put fairly tight constraints on the mass of the neutron star itself and the radius. So you can see that the radius is now constrained within about a kilometer or so, which is within a kilometer or two. So that's a very interesting result that one can obtain by X-ray timing. Coming to polarimetry, of X-rays was first started in 1975 through a Bragg reflection spectrometer, but there has been a long dormant phase, and it's only now dedicated X-ray polarimetry missions are being launched. In 2021, as I said, IXP was launched, and in 2024, XPOSAT has been launched. They use slightly different techniques to measure polarization. And the polarized emission originates from asymmetries in the source, and the processes that can lead to it include scattering or resonance scattering or synchrotron process, and this can be discerned by actually making polarization observations. Here's an example of a polarization observation from IXP of the supernova variant Cassiopeia A. These vectors that are drawn are the inferred direction of the local magnetic field, which one can do by doing the polarization observations. Again, multiband polarimetry with IXP plus polarimetry at other wavelengths, including optical and radio, can discern the flow of matter in the jet. You can see that magnetic field is actually aligned to the jet, and as the jet propagates to larger distances, the magnetic field tends to get somewhat disordered. This is AstroSat's observation of high energy polarization, 100 to 380 kilo electron volt of the trap pulsar. Point to note is the polarization vector as plotted in the sky plane. You see the polarization vector is more or less always in the same direction across the whole pulse. And as you see that this direction practically coincides with the projection of the spin axis of the pulsar, which is shown in the right arrow, which is just about to come. So the only way this is possible if the X-ray emission actually does not come from within the inner magnetosphere, but happens to come from the wind region outside. So the X-ray emission that we are seeing from this pulsar at these wavelengths, from these observations we can then tell that this X-ray emission is coming from somewhat region outside the inner magnetosphere. For accreting black holes, polarization can occur from various regions, from the scattered X-rays, Compton scattered X-rays from the disk or the corona, or non-thermal synchrotron emission from the jet. Recent observations, again from AstroSat, has shown that the polarization of such a black hole X-ray binary signals X1 has a very interesting progression as a function of photon energy. At low energies, for example, with IXP, you see somewhat lower polarization. At very high energies, with integral observatory, you see rather high polarization. And AstroSat in the mid-range shows something in between. And this can be interpreted as the coronal emission being the contributor in soft X-rays and jet emission in hard X-rays. And polarization allows us the ability to do this. We also observe gamma ray bursts, and here's an example of one gamma ray burst where you see two pulses of the burst, and one pulse has a thermal spectrum and is also unpolarized. Another part of the burst has a non-thermal spectrum and is polarized. So this again tells us that the emission mechanism of these two different parts of the same burst happen to be different. And without the polarization information, this would have been very difficult to do. So to summarize, X-ray astronomy is a relatively young field and developing rapidly, driven by space technology. Very hot gas and non-thermal energetic particles are main contributors to X-ray emission, and they're closely associated to compact object and violent phenomena. Imaging, spectroscopy, timing, and polarimetry at X-ray and gamma ray bands are unique probes of energetic sources. Several missions are currently active, providing diverse observational opportunities, and many new missions are also being planned, which I did not cover today, but down by you will come to know. More importantly, archival data from all these missions are publicly available, and that is a major resource for research even today, even if the data has been taken some years ago. I hope you will get an exposure to these aspects in the coming lectures. Thank you very much.
Thank you, sir, for such a wonderful lecture. I'm sure all of us learned something new, and we are extremely grateful for your time and the effort that you have put in. The participants may write their questions if they have any in the chat and ask us to unmute them if they want. Sir, we have a question. Shashank Singh is asking, what do we need? One second. What do we need polarimetry
for? Yes, so as I said, that there even from spectroscopy, timing, imaging, and so on, there are various aspects of the source and various aspects of the emission process which are not clear. For example, if in case of gamma ray bursts, we wouldn't know, we still have no clear idea as to whether the prompt emission of the gamma ray burst comes from thermal emission or non-thermal emission. And in case of accreting black holes, we don't know in which part of the black hole source different parts of the emission are coming from at different energies, whether some part is coming from the disk, some from the corona, some from the jet. And through polarization, we can actually make this distinction. We can find signatures which are different for these different parts of emission. And if polarization observations can tell us what the polarization is as a function of energy, we are able to actually make this distinction, which is not going to be possible by other means of observation.
Yes, sir, we have a few more questions. Sudeep Das is asking, can the X-rays received from place of high dark matter can be a possible source of for star formation?
So X-rays are radiation, right? So X-rays do not cannot act as source of star formation, but there is some indirect influence radiation can exert. Radiation can heat up gas, and radiation can also, if there is a strong radiation field, it can also produce a pressure by which the gas can move. And this motion of gas can then eventually result into condensing some parts and producing stars in an indirect way. But the X-ray radiation coming from the dark matter in the clusters of galaxies tends to be quite diffuse, and it does not have a pronounced effect in moving gas, which can then lead to star formation. There are other processes which are more efficient for it.
Yes, sir. Siddhartha is asking, what is the reason for quasi-periodic oscillation?
Yes. So any physical system, whatever physical system you may want to construct, or you may even construct in your laboratory, has some natural frequency of oscillation, normal modes. So if you create a metal box and you hit it with a hammer, the box is going to oscillate at its own natural frequency. So this is true of anything, including fluid flows. And so these oscillations then manifest as intensity fluctuations at those frequencies when you look at it, look at the radiation from it. Now, normally these oscillations are not long-lived. So the oscillation gets excited, it stays for a while, and then it stops. So in such a case, the frequency contained in this oscillation will not be a sharp frequency in the Fourier domain, but it will be widened by the coherence time of this oscillation. And this is the reason why these various different oscillations, which are natural frequencies of the system, come out, but they don't give you a very sharp spectral feature, but gives you a slightly broadened spectral feature, which we call quasi-periodic oscillation.
Sir, Pranjal Sengupta is asking, can thermonuclear flashes also occur during star?
During? Thermonuclear flashes. No, flashes will probably not occur. What will happen in star formation is, at the end of the star formation process, the center of the cloud that is collapsing to form star will start thermonuclear fusion, and then it will actually remain stable. The flash, it needs to be unstable. In a stellar system, the nuclear burning at the center, particularly the hydrogen burning, is stable. So it's not going to be a flash, but thermonuclear fusion will occur. Do you want me to take any more questions? You're muted. Can't hear you.
Am I audible, sir?
Yeah.
Yeah, so what was the last question? I got disconnected.
Yeah, so last question was, can thermonuclear fusion also occur during star formation?
Yes, sir. Yeah. So Lalit Kishore is asking about any tips for his future career in astronomy. He is currently pursuing bachelor in physics.
Yes, I mean, if you want to do astrophysics, the primary requirement is to learn your physics well. So you finish your bachelor's in physics. You can join a master's program somewhere which has astronomy in it, or you can do a master's program in physics and then join a PhD program in astrophysics as whatever is your preference. But at bachelor's level, doing a good physics degree is a pretty decent approach to doing astrophysics later.
Thank you, sir. Payal Nandi is asking, in some radio lobes of large-scale jet, we see a hard X-ray. ANS in some lobe we see, and in some lobe we see soft X-ray. What can be the reason for this?
Yeah, there could be multiple reasons for it. See, the hard X-ray, soft X-ray, these are slightly loose distinction. It depends on what energy you're talking about as the discriminator. So there is synchrotron emission, which produces radio emission and partly soft X-ray emission, depending on the local magnetic field. And then there is also a Compton component, which then upscatters these low energy photons to much higher energy photons. I actually showed you a picture of a spectrum of a blazar where you have lower energy emission, which is in radio and X-ray, radio optical X-rays, which is in soft X-rays, and then there is a Comptonized part of the emission, the synchrotron self-Compton emission, which is in hard X-rays and gamma rays. So a combination of these two can occur. In some cases, you may be able to see only one component or the other component, but because of these different physical processes that can occur in these radio lobes, you may see emission at different wavelengths, even in X-rays.
Sir, Abhishek is asking, you said an iron line is used to estimate the spin and mass. Isn't the thermal continuum regardless whether the iron line is present or not?
Thermal continuum is present. Iron line is over and above that. It's an emission line which rides over the thermal emission.
I think we are running out of time. I guess we can take a last question. Shashank is asking again, is it possible to distinguish a neutron star X-ray source from a black hole one?
Yes, there are several indicators which you can use. The main one being the overall X-ray spectrum of the source. The overall X-ray spectrum of the source tends to be somewhat different in case of black holes as opposed to neutron stars. I can't go into the details now, there is no time. But both spectroscopy and timing can distinguish between black hole and neutron star sources.
Thank you, sir. I apologize to the rest of the participants. Due to the limited time, we'll have to stop the Q&A session now. Once again, thank you, sir, for this amazing session.
Thank you for listening, and
yes, sir.
Have a great workshop. Bye-bye.
Thank you, sir. Bye.